On a daily basis, mathematicians use a symbolic language to communicate their ideas, not to be intentionally cryptic, but to express their ideas clearly, free from the ambiguities of the common language. Once a primitive idea has been cast into symbolic form, it may be manipulated to obtain more interesting and sophisticated ideas. So let us take a look at some of the most striking mathematical formulas and try and explain away the ideas conveyed by these formulas. So what is the value of this fraction here? It seems like the fraction goes on and never stops. So what is its value? You may say, well, I don't know what the value is. But a mathematics student has a very clever way of saying, I don't know what the value is. They say the value equals x. Observing the denominator of x, the fraction we'd like to solve for, it looks like that's another copy of the fraction. In other words, we say the fraction is self-similar. So it seems like the fraction x for which we like to find the value equals 1 plus the reciprocal of x. And this is a quadratic equation, and solving it we find a positive and a negative root. It looks like the fraction is positive, so we take the positive root here. Looking at the decimal expansion of this fraction, taking two digits at a time, you read 1, 1, 2, 3, 5, 8, 13, 21. They're the Fibonacci numbers. Perhaps you'll even know the formula for generating the nth Fibonacci number, though this strange formula involving irrational numbers when the terms of the sequence are actually just whole numbers. And by the way, why does this fraction generate the Fibonacci numbers? Is that just a fluke? There is such a concept called the generating function of a number sequence, where you put the terms of the sequence as the coefficients of this infinite series in the variable x. And by putting the Fibonacci numbers, you obtain this rational function in x, and this in turn can be decomposed into two geometric series, in fact a difference of geometric series. And by comparing the coefficients on the right power of the indeterminate x, we obtain this generating formula for the nth Fibonacci number. And by putting 1 over 100 in the place of x, we obtain this decimal, which generates the Fibonacci numbers two digits at a time. But there is one caveat. Observe here that 34 plus 55 should give 89, but here is 90, and this is the phenomena of overflow. Because the generating function gives the Fibonacci numbers two digits at a time, any Fibonacci number that are three digits would overflow this fraction. So that is interesting. And notice the analogy here, 1 plus root 5 over 2 is actually this continued fraction, so the concepts that we talk about are actually related. We should take a look at these identities discovered by Roger and Ramanujan. The first two are attractive because they take an infinite sum to an infinite product, and taking the ratio of these two, we obtain this very elegant continued fraction which sort of resembles the geometric series and even with a similar restriction, although I would really like to know how one takes an infinite sum to an infinite product. There is an interesting tale about Ramanujan. One day his friend goes to visit him in taxicab 1729 and asks him what is interesting about this number. Ramanujan thinks a bit and says, "It is the smallest number that can be written as the sum of two cubes in two different ways, and here you see it as the first equation on the corner of Ramanujan's notebook." Looking closely at these two equations, I hope some of you will be getting excited, because there is a certain theorem which asserts that no cube can be decomposed into the sum of two cubes, and just note how closely these two cubes sum to another cube. I once read a quote that says, "An idea that works only once is called a trick. An idea that can be used many times is called a method. But what Euler did to compute this sum is what I consider a hack." Surely you're looking at these whole numbers and wondering where the pi comes from. What Euler did was to try to discover this sum from the trigonometric sine function. In particular, Euler tried to express the sine function as a product involving its roots, much like the way you would write a polynomial in terms of its roots. For instance, if a polynomial had roots at 1 and 2, you would write the polynomial as a product x minus 1 times x minus 2 up to some constant. What Euler tried to do was the same for the sine function as a product of its roots at the integer multiples of pi, and that's where pi comes from. What Euler did was technically illegal because he applied a rule for polynomials to the sine function, which is technically not a polynomial, but still got a right answer. So that's why I call it a hack. But Euler, being a superb mathematician, was aware of the flaw in his technique, so he was not so quick at accepting his solution. But neither was he so quick at disposing his solution to the garbage can altogether, so he put a question mark and decided to examine his solution more carefully. He computed further down this series to see if it had agreed with his computation,
And yes, it did agree. He computed consequences of this series and obtained the sum of other series like he reports here in a publication. He found that indeed those series have agreed with his computations as well. Years later, Euler succeeded in proving his conclusion in a more rigorous framework. Yet our story illustrates the virtue of a mathematician in dealing with a doubtful finding, in the effort to compute further consequences to search of evidence in favor of or contradictions to disprove of that doubtful finding. Next, given a polygon, we can divide up its interiors into triangles, and for each given polygon, we can do so multiple ways. The triangle, there is one way, the square, there are two ways, 5 and 14, so on. These number of different triangulations form a numbered sequence called the Catalan numbers. You will note that a line segment can be considered as a degenerate triangle. Here we see that the sum of the reciprocals of the Catalan numbers has this sum. And again you notice the appearance of pi, and that is because this infinite series is related to the arcsine function, so that again the appearance of pi is related to a trigonometric function. Now we come to formulas of a different character. These quantities on the left are approximated by the quantities on the right. These approximate formulas are desirable because the quantities on the left are difficult to compute for larger values of n. And interestingly, these approximations become increasingly more accurate with larger values of the variable in question. Given a natural number n can be expressed as a sum of other natural numbers. This is like a partition of the number n, just like we can have partitions of polygons. The function p counts the number of distinct partitions of a given number n. The partition function may be asymptotically approximated by this formula, which was discovered by Ramanujan and his taxicab friend. You might be familiar with this symbol for the product of the first n natural numbers. Then you may be surprised to learn that you can compute the product of the first 0.5 natural numbers. That seems like a contradiction in terms. And this is in line with the mathematical spirit of generalization. Much like the trigonometric functions are initially defined for acute angles in the right triangle, and later extended to obtuse angles in the unit circle, a function originally defined for the natural numbers may be extended to a function defined for any numbers, and such that on natural numbers it resembles the factorial. When such a function is properly extended, it happens that the factorial of 1/2 may be computed in this general scheme to equal to root pi over 2. And we can show you the Desmos implementation of the generalized factorial, or more professionally known as the gamma function. And here is the asymptotic approximation of the factorial. In red, you see as the variable increases, the approximation becomes increasingly better. The factorial eventually outcompetes any exponential function. Here in the Stirling approximation that you see, this portion is almost an exponential function, except that the base increases with n, and it is for this reason that the factorial eventually outcompetes any exponential function, as we can here illustrate with one example, plotting the ratio between the exponential e to the x to x factorial. You see that this eventually decreases to 0, meaning that the x factorial is eventually much greater than the exponential e to the x. Now, I'm not going to explain this formula because it's just as famous as E equals mc squared, but I put it here because I'm plotting a joke which is upcoming. Perhaps counter to your intuition is that the sine function can be made to leave its usual comfort zone between -1 and +1, done by generalizing the sine function to take on values of complex number z. In this case, the sine function is no longer defined using a right triangle, but rather according to this general formula valid for any complex number z. When this generalization is done, the sine function may take on values arbitrarily far away from the origin, and this is made mathematically precise using this symbolism, which reads, for every positive number m, there exists a complex number z such that sine at z is further away from the origin than m. I'm not sure how up to date you are with the latest research into the most beautiful equation of all of mathematics, but some genius had recently succeeded in incorporating another famous constant into an equation alongside ei pi 1 and 0. That constant is another constant of Euler's, gamma, and the equation discovered was this. I'm sure this achievement is one that have out-Eulered Euler's equation. Now this gadget seems to be like a fashionable thing to keep at your desk. Start off with some beads, which travels down this grid and eventually lands in these cylinders. The relationship between how the beads lands in the cylinders and this continuous curve illustrates an important point in mathematics. In fact, you will see that the manufacturer has highlighted this triangle, which gives away the insight to the entire process, but we can draw this triangle in a more informative way. For a bead starting at the apex to reach the next row, one step is required, either to the left or to the right. For the bead to travel to the fifth row, 5 steps are required. If all steps are taken to the left, then 1, 2, 3, 4, 5. It reaches the leftmost position. If it needs to travel to this position, 2 to the right, then of the 5 steps, 2 must be steps to the right, and hence its 5 steps choose 2 steps. And from this you see that the probability distribution of the beads traveling down is really binomial. You will realize that the binomial distribution represented by the height of these beads collected in the cylinders is in close resemblance with this continuous curve which represents the normal distribution, or more commonly known as the bell curve. So the mathematical point illustrated here is a limit in probability distributions, that the binomial distributions approaches the normal distribution. And this takes us to the end of our episode.